The mantra that we should chant for the March 2015 examinations is the one that says, "Victory loves preparation." We are going to use this exam prediction to prepare and revise our Term 1 work. On the instructions and information of this question paper, I will advise that you read this information before you go to the exam. And when you get to the exam, do not waste time reading this information. Prepare this information before entering the exam. If there is any instruction here or information that you do not understand or you need clarity on, feel free to leave a comment for me in the comment section. I am more than happy to assist. Your 2015 March exam will definitely have question 1, which is based on multiple choice questions. To answer multiple choice questions or any question in physical sciences, we use the academic constitution that consists of 4 rules. The first rule is the I rule. The second rule is the C rule. The third rule is the A rule. And the last rule is the N rule. The I stands for interpretation, meaning we interpret the problem before we can solve it. Classification, C stands for classification, where we link the problem to the equations, the theory and concepts that we think go together with that problem. A stands for answering the question. I believe that if you have interpreted the question and classified it, it will be much more easier for you to actually answer that question. N stands for navigation of the answer, where we look at our answer and check if it makes sense, and also that there are no errors in our answer. For multiple choice question, we'll just check if it makes sense. But in terms of errors, I believe that this is not necessary because already we are given the answers here. We have to choose the correct one. I'm going to firstly start by reading the statement of multiple choice questions here, and we'll go through these questions. We are told here that various options are provided as possible answers to the following questions. Choose the answer and write only the letter A to D next to the question numbers 1.1 to 1.10 in the answer book. For example, if you are doing question 1.11, you only write C if you think C is the correct answer, because C would be an answer where there's a statement next to it. You do not write that statement, you only write the letter and the number. They further say here that each question has only one correct answer. So we are given 4 options here because we have A to D. But on these 4 options, A to D, there's only one that is correct. Question 1.1 says that an object is projected vertically upwards. Air friction is negligible. They then say the acceleration of the object at the maximum height. The acceleration of the object at the maximum height is. Now, an advice that I have for you in order to answer multiple choice questions is do not look at these answers. Try to answer the question without looking at the answer. Then come check and see if the answer that you calculated or have found is one of these options. So we are going to interpret this situation and say that we have an object here that is projected vertically upwards. This means it will go up here, reach the maximum height. Here at the maximum height, it will have a velocity of 0 meters per second, meaning it will stop for a very short time. Then it will change direction and go back vertically downwards to where it started. It could pass this point, or maybe it can stop here, we are not told. Now, if they say there is no air resistance or air friction is neglected, that would mean that the only force that is present here is the force of gravity, Fg. And we know that the force of gravity is directly proportional to the acceleration due to gravity. And because the two are directly proportional, it means that our acceleration due to gravity will point vertically downwards like that, because it will point in the direction of the force. And this acceleration is constant. We know this from Newton's law of universal gravity, that it does not change. So that means when the object goes vertically upwards, it experiences this acceleration. When it is at this point where it stops for an instant, it still experiences this acceleration. Even when it comes downwards, it experiences this acceleration. So this acceleration exists at every point of the motion. Even here, we still have this g. It's always a constant number throughout the motion of this object, and this acceleration is given by a constant number of 9.8 meters per second squared. Now, when we are at this point here, our acceleration, as I was just showing our diagrams, will also be g. Now, let us look at our options that we are given and see if we are able to answer the question. The first option says that the acceleration at the maximum height is 0. No, the acceleration is not 0 at the maximum height. It is a constant number of 9.8. They say here at B that it is a non-zero and point upwards. No, the acceleration will never point upwards. Remember, it points in the direction of the force of gravity. They say it is a constant and points downward. This makes sense, because this acceleration we said is a constant 9.8 and it always points downwards. D, they say non-zero and points downward. Okay, this also seems correct, but when they say non-zero, we don't know. We need more information to say whether is it changing or is it the same, because this number here, it is a non-zero as well. So the most accurate one between these two, I'll say it is C. So my answer would be C. So I am on question 1.1, and we're saying the answer is C. Now we can go to question 1.2. Question 1.2 says the position versus time graph of a ball that is thrown vertically upwards from the reference point is shown below. Now let us interpret this graph. When you look at this graph, you can see that at this point we have the time to be 0. We also have the position to be 0. And when the position is 0, we call this the reference point. The reference point basically is the origin, is where our position y is 0. That's where we start to measure our positions or our height. Now, when you look at this graph, you will recall that the motion from this reference point to here at the turning point, at this turning point here, represents the upward motion. So we said this is the upward motion. And this part of the motion from the turning point and going down there, it represents the downward motion. So this is where the projectile is going up, this is where it goes down. So obviously you can see that if you throw a projectile vertically upwards from the reference point, it will move from 0, go to the greatest height and come back to 0, because when the time here, at the total time t here, we have a position of 0, we have the reference point, meaning we came back to the reference point. So basically that's what I can say. I'm not saying a lot of things here because there's also there's much more that I can say with this graph. But I'm not going to touch on that because we studied vertical projectile motion graphs in detail. If you want more information on these graphs, go check the playlist of vertical projectile motion graphs. The question says then to us, which one of the following is the correct direction of motion? So here they're interested in the direction. Remember, to get the direction, we said that we use the standard form or the standard equation of a parabola. We said, this graph, when you're looking at it, is a parabola. We said we draw this graph from the equation final position is equals to 1 over 2g change in t squared plus initial velocity times change in t plus the initial position, not velocity, the initial position. And we said this graph is exactly the same as f of x is equals to ax squared plus bx plus c. Now when you compare these two graphs, you can see that the f of x is this part here, the a is this part here, the x squared is the t squared, the b is the initial velocity, the x here we said is the time, and the c is actually the initial position of the object. In this case, it is here at 0, it is the reference point. It is where the graph intersects the y-axis. Now if we want to find the direction of motion, we actually look at a, or we look at g, because we know that if our a is positive, we then have a happy graph. If our a is negative, we then have a sad graph. So if our a is positive, we have a happy graph, familiar faces. But if our a is negative, we then have a sad graph. These are the familiar faces. And when we look at our graph, it's actually a happy graph. It then tells us that our g here, because a is part of g. Now if we draw a vector of the g, we know that the g will always point downward and is given by 9.8 meters per second squared. And in this case, it means it is a positive 9.8 meters per second squared, because it gives us a happy graph from this equation when we look at 1 over 2g, which is our a here. That means in this problem, they've actually chosen, so this graph gives us a direction that they've chosen downward as positive. If I were to draw a reference frame to represent direction, it means downward is being taken as positive. It means vectors that go downward have been taken as positive. So our motion, the direction of our motion is that downwards is positive. Now when we look at our options, we can clearly see that A is the correct one because it says downward is positive. And in this case, I don't even need to look at these other ones because my answer is straightforward. So for 1.2, our answer is A. When we go to question 1.3, we are told that hot air balloon is descending vertically downwards at a constant velocity and a small metal ball is dropped. Ignore air resistance, very important statement. So if you look at this situation, you can see that we have a hot air balloon that is descending. To descend means it goes down, and it goes down vertically, and it moves at a constant velocity v. Now as it moves, there's a point where you can see here that a metal ball is being dropped by this person here. Now they say to us here, what is the speed of the ball the instant it is dropped? Now I would like to just draw this quickly. We have a hot air balloon here. This hot air balloon is actually moving vertically downwards with a velocity v. When it gets to some point here, the person in there drops a ball here. Now, there's a couple of things that we need to talk about. This person here, when they're here, is holding the ball. Now, as the hot air balloon is moving downward with this velocity v, this means the velocity of the ball is also v. The reason being is because of the person and the ball, they are inside the hot air balloon, meaning they move with the velocity of the hot air balloon. The easiest way to think about this is that you can always recall a situation when you are in a car. When the car moves, you actually move at the speed of the car. The same thing applies here. The metal ball moves at the speed of the hot air balloon, which is v. Now, when we get to this point, you'll find that the hot air balloon still moves with the velocity v, because remember, we said the velocity is constant. So it does not change from here to here. The velocity didn't change. Now, when this person drops the ball here, you will find that the ball will still have the velocity v here. The reason being is a concept called inertia, which we have defined it to be the natural tendency of an object to resist changes in its motion. What that means is that the metal ball, when it's dropped here, because it was moving at the velocity of v, the velocity of the hot air balloon, it will resist to change that velocity. It will want to continue moving at that velocity. It won't instantly change. That's why at that instant it is dropped, it will actually have the velocity v. It is only going to change its velocity when it has moved from this point to somewhere here. Then you'll find that the velocity has actually increased, because now remember, it is going vertically downwards and there's no air resistance. But at the instant where it is dropped, it actually still has the velocity of the hot air balloon. Because of inertia, it doesn't want to change that velocity or that speed. Now, so our options, when we look at them, they say double that of the hot air balloon. No, that cannot be true. The same as the hot air balloon. I mean, that's exactly what we said. So in question 1.3, our answer will actually be the letter B. It cannot be 0. And I know this one of 0, most of you would probably want to choose it, because we have said in projectile that when you drop a projectile, it means its initial velocity is 0. In this case, it does not hold. It is not true because of inertia. The ball was already moving. It was not 0. It was moving at the velocity of the hot air balloon. And it cannot be half either. Now we can move to question 1.4, which says that a watermelon moves vertically downwards at the speed of v. At some instant after being released from rest, the span speck moves at the same speed as the watermelon, as shown in the diagram. Now what's happening here is that we have a watermelon there that moves with a velocity of v. Then we have the span speck, which is released from rest. That's why the initial velocity here is 0. But at some instant as it has moved from there to here, it then has the velocity that is the same as the one of the watermelon. That's a simple situation, and it is possible for something like this to happen because the span spec will start with 0 and increases. Remember, the velocity increases here as it goes down. Then at this point, it will have that velocity of the hot air balloon. Remember, it accelerates with the acceleration of 9.8 as it goes down. Now, they say here that if the mass of the watermelon is 3 times that of the span spec, then the momentum of the span spec is. So we are actually looking for the momentum of the span spec if the watermelon has 3 times the mass of the span spec. Now, to do this, we'll then need to use our equations of momentum to then find what we are requested here. So now the very first thing that I'm going to do here is to actually write down my given information. We are told that the velocity of the watermelon is actually v, and the velocity of the span spec is also v at the point where we're looking at them. And we are told that the mass of the, if we say the mass of the span spec is m, right, we choose it to be m, it therefore means that the mass of the watermelon has to be 3 times that of the span spec, which is m. So it's going to be 3 times 3m, because this is 3 times the m which we have for the span spec. Now at this stage, I can then go calculate momentum because we want to compare the momenta here. I will say the momentum of the watermelon is going to be given by the mass of the watermelon times the velocity of the watermelon. Now when I substitute, I have actually 3m here and I have the v, because the velocity is v and the mass is 3m. I can do the same for the span spec to say that I have the mass ms vs, but my mass is m and the velocity is v. Now, if we manipulate these equations so that we say that where we see the mv, we can actually put the ps, the momentum of the span spec, because the momentum of the span spec is actually equals to mv. So that means here we have 3 ps and here we have pw. I just really substituted or replaced mv with the ps because we're saying ps is equals to mv. But remember, we are looking for the momentum of the span spec. That means I can divide by 3 both sides here so that I'm only left with ps on this side. So this would mean this side I will have actually 1 over 3 pw. So this would mean my momentum of the span spec is actually equals to 1 over 3 pw. Now when you look at our options here, you can see that A is actually the option that we're looking for because it is 1 over 3 pw, the way we actually have found it. So our answer here for 1.4 is actually A, and we can simply not do the other ones here because we found our answer. I want to share with you another way in which this question can actually be done. You can say that the mass of the watermelon is m. You can choose it to be m. That would mean that the mass of the span spec is equals to 1 over 3 m. Because remember, if I take 1 over 3 m, which is the mass of the span spec, and I multiply it by 3, remember we said here that the watermelon has 3 times the mass of the span spec. That means if I multiply this mass of the span spec by 3, I'm actually going to get the mass of the watermelon. And you can see that the 3 and the 3 cancel each other so that I have m. That's why I'm saying if you say the mass of the watermelon is m, then this one of the span spec has to be 1 over 3m. Now, You then would continue to say the velocity of the watermelon is equals to v, and the velocity of the sponge spike is v because they're the same. I'll leave it here for you to practice doing it and see if you get the same answer as we did, and see if your option will also be A as well. I'll jump to question 1.5. Question 1.5 says that two cars with masses x and y collide with each other while moving with velocities 5v and v respectively. Immediately after collision, the car with mass x moves in the opposite direction at 2v. So the x1 moves in the opposite direction at 2v. When the collision occurs in a closed system, the velocity of the car with mass y is given by this equation. Now, when I look at this problem, I can see that it is actually the law of conservation of momentum. Because I have a system, I have more than one object interacting with each other. You have two masses, x and y. And these masses, they actually collide with each other in a closed system. So the momentum must be conserved. Now, what I'm saying is that if you actually take this information and say this is M1, M2, and say this is V1 initial and V2 initial, and then come and say this would be M1, and this will be the final velocity of x. So because we said x is M1, it means now this would be V1 final, and it's going to be a negative 2v. And you then use the equation of the law of conservation of momentum. So you say M1 V1 initial plus M2 V2 initial is equals to M1 V1 final plus M2 V2 final. I mean, this is the law of conservation of momentum. We said here it is going to be conserved because it's a closed system. If you then come and substitute these numbers, x for M1, y for M2, V1i, and then you substitute the v to be the V2i, and here you have V1 final to be negative 2v because it goes in the opposite direction. You put all these variables here, you'll find that the V2 we don't have. If you then solve for V2, if you solve this equation for V2 final, you will get this equation. That's where it comes from. Because in a closed system, that's what they said, in a closed system we should get this equation because we have to use the law of conservation of momentum. I want you to try and do it on your own, just for practice purposes, to see if you'll get this equation. Now, in this question, they then say, look, if the masses of the cars are the same, the velocity of mass y after collision is. Now, what we're saying here is that if the masses are the same, remember we said here that M1 is equals to x and M2 is equals to y. That's what we said here at the beginning of the problem. And we get this equation. We are now saying that if the two masses are the same, that would mean that if M1 is the same as M2, this would mean that x is the same as y. They then asking us what is the final velocity, or the final velocity of y after collision. So what would be the V2 final? Well, we know that V2 final is defined by this equation, V7x plus y over y. Now what that means is that I can now write the x as a y because they're really the same. So that I have V7y, where I see a y, I put an x because they're the same, plus y all over y. Now this would mean I have a V, the 7y plus y, it should give me 8y, and I'm still dividing here by a y. You can see here clearly that the y and the y would cancel, and at the end of the day, I'm only going to be left with V2 final to be 8v. So what this means is that the final velocity of mass y would be 8 times its velocity before collision, because remember, the y mass has the velocity of v before collision. So if the masses are the same, it means it's going to be 8 times. This velocity would have increased by 8 times. And on our options here, we can see that option B is actually the correct option. 1.5. Our option would be a B. If we continue and look at question 1.6, we are told that an object is dropped from point A and moves straight downwards until it strikes the ground. When it passes points B and C, it has speeds of 3v and 6v respectively. Ignore the effects of air resistance. Now what we're saying here is that we are dropping an object here at B, and you can see that B is the reference frame because it's 0 meters. So here we drop it with a velocity of 0 meters per second, because when you drop an object, it has a velocity of 0. It then goes downwards. It makes a trajectory that goes downwards like that until it reaches the ground. However, we are told that when it gets to this point here, B, we have a velocity. I'll call it initial velocity because from here to here it changes. So the initial velocity here is going to be equal to 3v, and remember the velocity is increasing as it goes downwards because the acceleration and the velocity are in the same direction here. The force of gravity is going downwards, so it's pushing it downwards. So that's why it moves from 0 and increases, and this makes sense that we'll have a velocity of 6v. Now they say point A is the origin. I think I noted that, when I was reading the diagram. Now the question says to us that the impulse of the object between points B and C, between this point and this point, is. So basically they want us to calculate the impulse between those 2 points. Well, to get the impulse, we know that the impulse is defined as, I for impulse is defined as the product of the net force and time. But we also know from the impulse momentum theorem that it is given by the change in momentum. Now I'm coining in the change in momentum because I can see I have velocities. I don't have time, and I don't have also the net force. This would mean that we'll translate this to be m minus v final, m times v final minus v initial in brackets like that. And I can then now here substitute. Obviously this object has the mass, that's why the m is there. I can substitute now my values. The final velocity we said it is 6v, and the initial velocity we say here it is 3v. Now, very important, this equation requires us to choose direction, and I realized that I didn't choose direction as I'm going along. Because already I've started this question, I will cleverly choose downward to be positive, so that these velocities here, they're positive since they're going downwards. Remember, these are vectors that are going downwards like that. Now when I substitute here, I'll have the final velocity of 6v, which is positive, and 3v, which is positive. Remember, you can choose downward to be negative, in which case we'll have a negative here and you'll have a plus as well there. So direction is up to you. Now when we solve this, you can see that we're going to have m, and in here we're going to have a 3v. At the end of the day, we're saying the impulse is going to be equals to 3mv. And we know that mv is actually the momentum. So this means that we're going to have 3p. So the impulse of these objects when they pass point B and C is 3 times the momentum of the object. The options that we have here, they say to us that the impulse is 3 times its momentum and in the upward direction. Now remember, we got a positive answer here. Our answer is positive. That means this is downwards. Our direction is downwards. So this one cannot be correct because this ball clearly doesn't have a momentum or the impulse that goes downward. Our impulse should go in the downward direction. It should be a vector that goes vertically downwards. It cannot be 6 times, so these two are out. We're saying here 3 times its momentum and in the downward direction. So C is actually is our correct answer. So for 1.6, the answer is D. 1.6, our answer is D. We then move to the next question, which is question 1.7. We are told here that the net force versus acceleration graph of an object in motion is drawn below. So the graph that we are given here is the graph of the net force versus acceleration. Obviously, when we start by saying the net force, it means it should be here on the vertical axis. It is our dependent variable. And the one that is on the x-axis is our independent variable. And we can see here that the net force is measured in kilogram meters per second squared. That's another SI unit for the net force, right? This is the same as Newton. And the acceleration here is measured in meters per second. Now, when we look at this graph, we can see that it's a linear graph, it's a straight line, right? Which begins at 0, where the acceleration and the net force are 0. And as the acceleration increases, the net force also increases. As the acceleration increases, the net force increases. And you can see that these results, we expect them to. Okay, in other words, this is the relationship of Newton's second law, where we said the net force is directly proportional to the acceleration. And we said this is given by the formula net force is equal to the mass times the acceleration. Now, this formula, when you look at it, is a straight line function. We're basically saying the net force is a function of acceleration. As the acceleration changes, the net force also changes. And we can see that they increase linearly, just like that. So another way of looking at this, you can say it's a function of y is equal to mx, right? And our c here actually is 0. Is 0 because our y-intercept is 0. That's why we only have mx here. The m here represents the mass. The gradient is the mass, meaning the gradient of this straight line will give us the mass. If I take the gradient of this straight line, we'll get the mass of the object. And our x here is the A and the y is the net force. I think this is just how you'll interpret the graph before you can even attempt answering the question, because your answer would come from this interpretation really. Now they say here, which statement below about point A is correct? About point A is correct description of the motion. Now if we look at point A, which of these options are correct? Now, but one thing that I can tell you before I even read these options is that at A we said that the acceleration is 0. Now, when the acceleration is 0, it means we are in equilibrium. We have the motion that is called equilibrium. Remember, equilibrium is when the acceleration and the net force are 0, because the acceleration and the net force are 0 here. And equilibrium would mean that an object is stationary. It does not move. Our object is stationary. It does not move. It also means the object is actually moving, but with a constant velocity. Remember, when an object moves with a constant velocity, the acceleration is 0 and therefore the net force is 0. So at this point, it means our object is either stationary, not moving, or it is moving but with a constant velocity. That's the motion that we can describe using the information that is on point A. Now let us look at our options. They say here that on A, the velocity of the object is constant. That's true because it's exactly what we have here in equilibrium. It's one of the options of equilibrium. So I'm going to choose my answer here to be A. We can check the other ones just to make sure that there is no any other ones that clash with A. So the velocity cannot increase, the velocity cannot decrease at A really, because the acceleration is 0 and the net force is 0. And the acceleration is constant. Well, the acceleration is 0 here, even though 0 is a number that is constant, it does not change. But, the best option here would be that the velocity is a constant. Now we go to 1.8. Question 1.8 says to us that mass 1 is connected to mass 2 with an inextensible string of negligible mass. Now we are saying here that we have connected this object and that object with a string that does not have mass. We can ignore its mass, because remember, when we ignore its mass, we then allow this system to behave such that a couple of things become the same. The tension here becomes the same, right? And the acceleration as well becomes the same. Now they further say here that the net force F is applied. This is this force here, and the system moves to the left as shown below. Now when we apply this force, the system begins to move and it goes to the left. That's why we have acceleration A1, which is the acceleration of the first object, and acceleration A2, which is the acceleration of the second object. Now this we know, when you look at this, it's Newton's second law, or Newton's laws of motion, where we're looking at systems. So we have more than one object, and we know those are problems where we do simultaneous and all that. Now they say here that choose the correct statement regarding the acceleration. So our statement is regarding the acceleration of the masses. Okay, I have to look at these options, but one thing that I can tell you quickly is that in such a situation, A1 is equals to A2, and usually we just give them the letter A, because they're the same. They have the same magnitude of A. So what we're saying is that the two masses, they accelerate at the same rate. They change their velocity at the same rate, because they are connected by a light inextensible string. The string has mass that can be ignored. So they move as a system, as if they are one thing, even though they are not the same thing. So on my options, at least in terms of acceleration, that's what I have to see. They say here the acceleration of mass 1 is greater. No, it is not greater. The acceleration of mass 1 is less. No, it is not less. The acceleration of both, no, the acceleration is not 0. I mean, these things, they are not stationary and they're not moving at a constant velocity. So they don't have a 0 acceleration. This seems to be the correct answer, because all of these are wrong. They say here the acceleration of mass 1 is equal to acceleration of mass 2. That's exactly what we said here. So our answer here will be D. 1.8, the answer will be D. Now when we look at question 1.9, they say to us that a passenger is sitting on a bus seat. The Newton's third law of motion pair force to the gravitational force acting on the passenger is, okay, let me break this question down. So we are saying here that we have a passenger who's sitting on a seat. So this would mean that they are inside a bus, because they're sitting on a seat of a bus. We are saying here, remember that Newton's third law of motion has pair of forces that are equal in magnitude but point in the opposite direction. So we are told here that the force that acts on the passenger is the gravitational force. That means that we have the earth here, the bus is moving on the Earth's surface, right? This is the Earth, and this is the passenger. Now, the Earth, obviously, we all know that it attracts every object towards its center. So the Earth exerts a force here on the passenger. This will be the force of the Earth on the passenger. And this force is the gravitational force release defined by Newton's law of universal gravity, right? It pulls that passenger downwards towards the center. Now, if we want a pair that goes with this force, right, the Newton third law pair, right, it will be a force that should have the same magnitude but point in the opposite direction. We know that Newton's third law says that if the Earth exerts a force on the passenger should also exert a force on the Earth. In other words, the passenger will also attract the Earth with a force that has the same magnitude as this force but points in the opposite direction. So this will be the force of the passenger on the Earth. And remember that the Newton's third law pair of forces, they act on different objects since they are interacting objects. So the Earth exerts a force on the passenger, then the passenger will exert the same amount of force on the Earth but in the opposite direction. You can see that this vector is going down but this vector is going upwards. So that's the option that we have to see here. That's a pair that we have to see. On A, they say the force of the seat on the passenger. No, the seat is not part of this. We are not told anything about a force that is on the seat. So that's wrong. The force of the seat, again, the seat is not part of this. We are not told anything about the seat. They say here the force of the passenger on the Earth. We actually expected that, right? It's the force of the passenger on the Earth. So question 1.9 is going to be C. Now, none of the above, well, that's wrong, obviously. The last question, question 1.10, says to us that an object moves with a constant speed on a horizontal plane. Now, just to demonstrate this, I'm going to draw an object like this. When we say an object moves at a constant speed, it means its initial velocity maybe is a number v. And this object moves on a horizontal plane, right? It goes to that direction. Say it gets to some point here. When we check its final velocity, it will still be the same v, because remember, we are saying that this velocity is constant, meaning it does not change. So it is as it's going along here, it's actually moving with the same velocity at every point. It does not change. That's what it means. Now they say here, which one of the following combinations is true about the motion of the object? Which one of these? Now, the combinations that we have is the acceleration, is the net force, is the change in momentum, and is the impulse. I think to answer this question, I'll look at all of these. I'll start first by looking at the acceleration, followed by the resultant force, followed by the change in momentum, and lastly, on this side, we will have our impulse. Now, when we want to calculate the acceleration, we know that the acceleration is given by A is equals to final velocity minus initial velocity over change in time. And we are saying here that our final velocity is v because, it does not change. It's the same velocity as the one we started. So our initial velocity is also v, change in t. Now you can see here that if you say v minus v, we get 0 here and that. So this means our acceleration is equal to 0. And we actually expected this answer because we know that when an object moves at a constant speed, the acceleration is 0. So this is just me showing you where it comes from. Now, the second part is the net force. Well, we know that the net force will also be 0 because we can take that from Newton's second law, where we put the acceleration, which we found here to be 0. And that would mean then we have our net force to be 0 as well. So our net force will also be 0. We know this from Newton's second law. That's why I'm using the formula of Newton's second law. The other thing that we have is the change in momentum. We know that change in momentum is actually defined as, maybe let me extend this here because I realized that my equation of change in momentum is a bit lengthy. So change in momentum is defined as v final minus v initial. And we can see that we'll have the m, and our v final will be v, our v initial will be v, and this would mean I'll have m times a 0. Now if you say m times a 0, it means my change in momentum is actually 0 kilogram meters per second. So the change in momentum is also 0. So there's no change in momentum when an object moves at a constant velocity. The last one actually is the impulse. Obviously, if we are saying here that our change in momentum is 0, it means the impulse will also be 0, because the impulse momentum theorem says the two that are the same, the two that are the same. So here we'll also have a 0 because the impulse is equal to the change in momentum. And so if the change in momentum is 0, it means the impulse is also going to be 0. Even if you can use the equation, let me use this part here. Even if we can say the net force times change in time, which is the impulse, you will find that our net force is 0 and we have change in t here, because we said our net force is 0 here. So you will still get the change in p to be 0, or the impulse to be 0. Our impulse to be 0, or the change in momentum to be 0. We can also look at the net force from the original version of Newton's second law. The definition of net force in terms of impulse. You can clearly see that the net force will be 0 as well, because we are saying that our change in momentum is 0, and this would also give me 0 Newton. So those are all the possible ways in which we can find all these combinations. So all of these combinations are 0 actually. If you have noticed, the acceleration is 0, net force is 0, the change in momentum is 0, the impulse is also 0. So my option here cannot be A, it cannot be B, 0, 0, 0, 0. It is actually indeed C. Our answer is C. And there's no decrease or any of that. These are wrong.